For estimating branch circuit wiring in commercial structures, consider these shortcuts and advice. When estimating conduit in cable, utilize a unit length method. Assign a standard length, such as 50 feet, to each device or fixture. Multiply this length by the number of devices or fixtures to estimate the total conduit or cable length. Consider the building layout. Account for horizontal and vertical runs, as well as obstacles like walls, ceilings, and partitions. Add 10 to 15% for waste and contingencies. This allows for extra material to account for unexpected route changes or damage. For junction box estimation, estimate one junction box per 150 to 200 square feet of floor area. This provides a starting point for sizing your junction boxes. Consider device spacing. Place junction boxes at convenient intervals, for example, at 4-foot centers, to minimize conduit lengths and wire splices. Allow for future expansion. Provide additional junction boxes and conduit space for potential device additions or upgrades. For efficiency, utilize electrical design software. Several software programs can automate the estimation process and provide accurate quantities. Break down the project into smaller areas. Estimate one level or section at a time to prevent mistakes and reduce errors. Leverage past experience. If you have worked on similar projects, refer to previous estimates as a guide. Consult with a licensed electrician. An electrician can provide expert advice and help you refine your estimates. Use estimating templates. Create customizable templates that include standard quantities for typical devices and fixtures. Allow for review and feedback. Share your estimate with others, such as project managers and engineers, for review and feedback. For additional considerations, think about lighting loads. Estimate the lighting power density in watts per square foot based on the building type and usage. Adhere to electrical code requirements. Ensure your estimate meets the requirements of the National Electrical Code, or NEC, and local codes. Account for voltage drop. Calculate voltage drop over the entire circuit to avoid excessive voltage loss. Consider ventilation and heating, ventilation and air conditioning, or HVAC systems. Consider the power requirements for ventilation fans, air handlers, and other HVAC equipment. Account for any specialty lighting systems such as track lighting and fluorescent fixtures, security systems, or data infrastructure. The National Electrical Code, or NEC, is a comprehensive set of standards that governs the safe installation of electrical wiring and equipment. Adhering to the NEC is crucial for ensuring the safety of people and property. Some key aspects of the NEC relevant to branch circuit wiring in commercial structures are firstly, conductor sizing, which involves selecting the appropriate wire gauge based on the ampacity of the circuit and the type of insulation. NEC Table 310.15 provides ampacity ratings for various conductor types and sizes. Secondly, overcurrent protection, where branch circuits must be protected by circuit breakers or fuses sized according to the ampacity of the conductors. The NEC specifies maximum overcurrent protection ratings for different conductor sizes. Thirdly, grounding, where all non-current carrying metal parts of electrical equipment must be properly grounded to provide a low impedance path for fault current. The NEC outlines specific grounding requirements for different types of equipment and systems. Fourthly, conduit fill, where the number of conductors allowed in a conduit is limited by the NEC to prevent overheating and ensure easy wire pulling. NEC Chapter 9 provides tables for calculating conduit fill. Fifthly, box fill, where the NEC specifies the maximum number of conductors and devices allowed in an electrical box to prevent overcrowding and ensure proper connections. Sixthly, spacing and support, where the NEC requires that conductors and cables be properly supported and spaced to prevent damage and ensure proper ventilation. Seventhly, identification, where the NEC requires that all conductors be properly identified with color coding or other markings to indicate their purpose. Eighthly, emergency systems, where the NEC has specific requirements for emergency lighting, power, and fire alarm systems to ensure they operate reliably during a power outage or fire. Ninthly, healthcare facilities, where the NEC has additional requirements for electrical systems in healthcare facilities to protect patients and staff from electrical shock and other hazards. Tenthly, hazardous locations, where the NEC has specific requirements for electrical equipment and wiring in hazardous locations where flammable gases, vapors, or dust may be present. Understanding voltage drop is crucial for designing efficient and reliable branch circuits, especially in commercial structures where long runs of wiring are common. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, lights to dim, and motors to overheat. Firstly, conductor size. Larger conductors have lower resistance, which reduces voltage drop. Selecting the appropriate conductor size is the most effective way to minimize voltage drop. Secondly, circuit length. Longer circuits have greater voltage drop. To minimize voltage drop, keep circuit lengths as short as possible. Thirdly, load current. Higher load currents result in greater voltage drop. Reducing the load current or using multiple circuits can help to minimize voltage drop. Fourthly, power factor. Low power factor increases voltage drop. Improving the power factor of the load can reduce voltage drop. Fifthly, allowable voltage drop. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Sixthly, voltage drop calculation. The voltage drop can be calculated using the following formula: voltage drop equals current times resistance, where current is the current flowing through the conductor in amps, and resistance is the resistance of the conductor in ohms. Seventhly, conductor resistance. The resistance of a conductor depends on its material, length, and cross-sectional area. Copper conductors have lower resistance than aluminum conductors. Eighthly, temperature. The resistance of a conductor increases with temperature. Voltage drop calculation should be based on the maximum operating temperature of the conductor. Ninthly, parallel conductors. Using parallel conductors reduces the overall resistance of the circuit, which minimizes voltage drop. Tenthly, voltage drop compensation. Automatic voltage regulators can be used to compensate for voltage drop and maintain a constant voltage at the load. When estimating lighting loads, it's important to consider several factors to ensure accurate and efficient design. Lighting power density is a key metric for estimating lighting loads. It represents the amount of power, in watts, consumed by lighting per square foot of floor area. The lighting power density varies depending on the building type, usage, and local energy codes. Space type is also important. Different spaces have different lighting requirements. For example, offices typically require higher lighting levels than storage areas. Task lighting is needed for specific tasks, such as reading or assembly, requiring higher illumination levels. Control systems like occupancy sensors, dimming controls, and daylight harvesting systems can significantly reduce lighting energy consumption. The NEC and local energy code set requirements for lighting power density and control systems. Ballast type, where electronic ballasts are more energy efficient than magnetic ballasts and can reduce lighting energy consumption. Lamp type, where light emitting diodes, or LEDs, are the most energy efficient lamps and have a longer lifespan than incandescent or fluorescent lamps. Lighting layout and proper layout of lighting fixtures is essential for providing adequate illumination and minimizing energy consumption. Maintenance factors account for the reduction in light output over time due to lamp aging and dirt accumulation. Energy audits can identify opportunities to reduce lighting energy consumption. Rebates and incentives, where many utilities offer rebates and incentives for installing energy-efficient lighting systems. The NEC specifies the requirements for branch circuit wiring in commercial buildings, including conductor sizing, overcurrent protection, grounding, and wiring methods. Understanding these requirements is essential for ensuring the safety and compliance of electrical systems. Conductor ampacity is the maximum current that a conductor can carry, without exceeding its temperature rating. The NEC provides tables that list the ampacity of various conductor sizes and types. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. The NEC specifies the maximum overcurrent protection rating for different conductor sizes. Grounding is the process of connecting non-current carrying metal parts of electrical equipment to ground to provide a low impedance path for fault current. The NEC specifies the grounding requirements for different types of equipment and systems. Wiring methods, where the NEC recognizes several different wiring methods, including conduit, cable, and raceway systems. Each wiring method has its own advantages and disadvantages, and the selection of the appropriate wiring method depends on the application. Conduit fill is the percentage of the cross-sectional area of a conduit that is occupied by conductors. The NEC limits the conduit fill to prevent overheating and ensure easy wire pulling. Box fill is the maximum number of conductors and devices that are allowed in an electrical box. The NEC specifies the box fill requirements for different types of boxes. Spacing and support, where the NEC requires that conductors and cables be properly supported and spaced to prevent damage and ensure proper ventilation. Identification is the NEC requires that all conductors be properly identified with color coding or other markings to indicate their purpose. Inspections, where electrical systems must be inspected by a qualified inspector to ensure compliance with the NEC and local codes. HVAC systems in commercial structures require a significant amount of electrical power to operate. Estimating the power requirements for these systems is essential for ensuring that the electrical system is adequately sized. Motor horsepower, where HVAC systems typically use motors to drive fans, pumps, and compressors. The horsepower rating of these motors is a key factor in determining the power requirements. Voltage and phase, where HVAC equipment is typically powered by 208 volts, 240 volts, or 480 volts, three-phase power. Air conditioning load, where air conditioning systems consume a significant amount of power, especially during peak cooling periods. Heating load, where heating systems may use electric resistance heaters, heat pumps, or gas-fired furnaces. Ventilation load, where ventilation systems consume power to circulate fresh air and exhaust stale air. Control systems, where HVAC systems typically use control systems to regulate temperature, humidity, and airflow. Efficiency ratings, where HVAC equipment has efficiency ratings such as Seasonal Energy Efficiency Ratio, or SEER, for air conditioners, and Heating Seasonal Performance Factor, or HSPF, for heat pumps. These ratings can be used to estimate the energy consumption of the equipment. Diversity factors that can be used to account for the fact that not all HVAC equipment will be operating at its maximum load at the same time. Energy audits can identify opportunities to improve the energy efficiency of HVAC systems. Rebates and incentives, where many utilities offer rebates and incentives for installing energy-efficient HVAC equipment. Special systems in commercial structures, such as fire alarm systems, security systems, and data infrastructure, have unique electrical requirements that must be considered when estimating branch circuit wiring. Fire alarm systems, where fire alarm systems require a dedicated power supply and wiring to ensure they operate reliably during a fire. Security systems, where security systems, such as access control systems and surveillance cameras, require power and wiring to operate. Data infrastructure, where data infrastructure, such as computer networks and telecommunications systems, require power and wiring to support their operation. Emergency power, where special systems may require emergency power to ensure they continue to operate during a power outage. Battery backup, where some special systems may require battery backup to provide power during short-term power outages. Uninterruptible power supplies, where uninterruptible power supplies or UPSs can provide continuous power to critical special systems during power outages. Surge protection, where special systems may be susceptible to damage from power surges, so surge protection devices should be installed. Grounding, where special systems must be properly grounded to prevent electrical noise and ensure proper operation. Codes and standards, where special systems must comply with applicable codes and standards such as the National Fire Protection Association, or NFPA, standards for fire alarm systems. Documentation, where special systems should be properly documented, including wiring diagrams, equipment specifications, and operating procedures. Testing and maintenance, where special systems should be regularly tested and maintained to ensure they are operating properly. Track lighting and fluorescent fixtures are common types of lighting in commercial structures. Estimating the wiring requirements for these fixtures requires consideration of several factors. Track lighting, where track lighting systems consist of a track with multiple lighting fixtures attached. The wiring must be sized to accommodate the total load of all the fixtures on the track. Fluorescent fixtures, where fluorescent fixtures require a ballast to regulate the current flowing through the lamp. The ballast must be properly sized for the lamp being used. Voltage, where track lighting and fluorescent fixtures are typically powered by 120 volts or 277 volts power. Wiring method, where track lighting and fluorescent fixtures can be wired using conduit, cable, or raceway systems. Control systems, where track lighting and fluorescent fixtures can be controlled by switches, dimmers, or occupancy sensors. Energy efficiency, where track lighting and fluorescent fixtures are available in energy-efficient models. Codes and standards, where track lighting and fluorescent fixtures must comply with applicable codes and standards, such as the NEC and local energy codes. Layout, where the layout of track lighting and fluorescent fixtures should be carefully planned to provide adequate illumination and minimize energy consumption. Maintenance, where track lighting and fluorescent fixtures should be regularly maintained to ensure they are operating properly. When estimating the total quantity of conduit needed, start by determining the length of each conduit run. To do this, measure the distance between the electrical boxes, panels, or equipment that the conduit will connect. For straight runs, the measurement is straightforward. However, for runs with bends or offsets, you'll need to account for the additional length required for the bends. Use a conduit bender to create accurate bends, and be sure to add the appropriate length for each bend based on the bender's specifications. Next, determine the number of bends in each conduit run. Each bend adds to the overall length of the conduit needed. Common bends include 90-degree bends, 45-degree bends, and offsets. An offset is a combination of two bends used to move the conduit around an obstacle. To accurately estimate the total length of conduit, use the following formula: total conduit length equals sum of straight run lengths plus sum of bend lengths plus waste factor. It is important to consider the size of the conduit. The size of the conduit depends on the number and size of the wires that will be installed inside it. The NEC specifies the maximum number of wires allowed a conduit of a given size. Consult the NEC tables to determine the appropriate conduit size for your application. Next, account for couplings and connectors. Couplings are used to join two sections of conduit together, while connectors are used to attach the conduit to electrical boxes or equipment. Add the appropriate number of couplings and connectors to your estimate. Finally, add a waste factor. It's always a good idea to add a waste factor to your conduit estimate to account for mistakes, cut-offs, and unexpected changes. A waste factor of 10% to 15% is typically sufficient. By following these steps, you can accurately estimate the total quantity of conduit needed for your electrical project. Estimating the length of wire needed for branch circuits in commercial structures involves a systematic approach to account for all the necessary components and factors. Firstly, determine the number of devices and fixtures. Start by counting the number of electrical devices and fixtures that will be connected to the branch circuits. This includes lighting fixtures, receptacles, switches, and any other electrical equipment. Secondly, measure the distance between devices and fixtures. Measure the distance between each device or fixture and the electrical panel or junction box that will supply power to it. This measurement should include the horizontal and vertical distance, as well as any additional length needed to navigate around obstacles or through walls. Thirdly, account for conduit or cable runs. Determine the type of conduit or cable that will be used to run the wiring. If conduit is used, add the length of the conduit runs to the total wire length. If cable is used, estimate the cable length needed to reach each device or fixture. Fourthly, add extra wire for connections. Add extra wire to each connection point to allow for proper termination and splicing. A general rule of thumb is to add at least 6 inches of extra wire at each connection. Fifthly, calculate the total wire length. Calculate the total wire length by adding up the length of all the individual wire runs, including the extra wire for connections. Sixthly, account for voltage drop. Consider the voltage drop in the circuit, especially for long runs. If the voltage drop is excessive, you may need to increase the wire size to reduce the voltage drop. Seventhly, add a waste factor. Add a waste factor to account for any waste or mistakes that may occur during installation. A waste factor of 10% to 15% is typically sufficient. Eighthly, determine the number of wires required. Determine the number of wires required for each circuit, including the hot, neutral, and ground wires. Ninthly, calculate the total wire quantity. Calculate the total wire quantity by multiplying the total wire length by the number of wires required for each circuit. Tenthly, consider the wire type. Select the appropriate type of wire for the application, such as THHN, THWN, or XHHW. The wire type should be suitable for the voltage, current, and environmental conditions. Additionally, always consult the NEC for specific requirements and guidelines related to wire sizing and installation. These steps will help to accurately estimate the length of wire needed for branch circuits in commercial structures. Estimating the number of junction boxes needed for branch circuits in commercial structures requires careful consideration of several factors. The first thing to consider is the NEC requirement. The NEC specifies the maximum number of conductors and devices that can be installed in a junction box of a given size. Consult the NEC tables to determine the appropriate size of junction boxes for your application. Secondly, consider the number of splices and terminations. Junction boxes are used to make splices and terminations in electrical wiring. Estimate the number of splices and terminations that will be required in each branch circuit. Thirdly, consider the layout of the circuits. The layout of the branch circuits will affect the number and location of junction boxes. Place junction boxes at convenient locations where splices and terminations can be easily made. Fourthly, consider the type of wiring method. The type of wiring method used, such as conduit or cable, will affect the number and type of junction boxes needed. Fifthly, consider the size of the conductors. The size of the conductors will affect the size of the junction boxes needed. Larger conductors require larger junction boxes. Sixthly, consider the accessibility of the junction boxes. Junction boxes should be located in accessible locations where they can be easily inspected and maintained. Seventhly, consider the future needs. Plan for future expansion and add extra junction boxes to accommodate future wiring needs. Eighthly, consider the cost. The cost of junction boxes can vary depending on the size, type, and material. Choose junction boxes that are cost-effective and meet your needs. Ninthly, consider the environment. The environment in which the junction boxes will be installed will affect the type of junction boxes needed. For example, junction boxes installed in wet locations must be watertight. Tenthly, consider the local codes. Local codes may have additional requirements for junction boxes. Consult your local codes to ensure compliance. Estimating the number of junction boxes is an important step in estimating the cost of an electrical project. By following these guidelines, you can accurately estimate the number of junction boxes needed for your application.